2, we look at expectation and variance, and variance for multivariate. Normal distribution. We start with expectation. Let x1, x2, all the way to xn denote n jointly distributed random variables with the joint density function. So that it has a joint density function f of x1, x2, all the way to xn. Then the expected of g x1, x2, all the way to xn, it's the same as getting integral negative infinity to infinity, all the way to integral negative infinity to infinity, g of x1, all the way to xn, f x1, all the way to xn, then dx1, all the way to dxn. We look at an example. Use the previous example. Let x, y, z denote 3 jointly distributed random variables with joint density function f of x, y, z is equals to 12 over 7 x squared plus yz for x, y, z, and it's 0 elsewhere. So we want to determine expected of x, y, z. So the solution to this, we are going to get expected of x, y, z as integral. We have the 3 variables in question. Then we put whatever we are looking for. It's expectation here, x, y, z. Then we put the distribution, that is 12 over 7, x squared plus yz, and we are differentiating with respect to each of the random variables. Opening up this, then we have integral. Open up the brackets, so we can first factor out 12 over 7, so that if I multiply this and this, I get x cubed yz. If I multiply this in the second part, I get plus x y squared z squared. Then we are integrating with respect to d to x, y, and z. So we carry out the integral. First we start with x, that will be 12 over 7. Then I'm remaining with the other two integrals. With respect to x, this one, it become a quarter x power 4, yz. Then plus, this will be a half x squared, y squared, z squared. Make replacements for x is equals to 0 and x is equals to 1. We'll now remain with respect to z, to x, and with respect to y. So this becomes 12 over 7, integral 0 to 1, 0 to 1. Then if I make replacements for 1, it disappears in both cases, so that we have a quarter yz plus a half y squared, z squared. Then we are integrating with respect to y and z. So now, if we differentiate with respect to y, we are going to have 12 over 7. Then we remain with the integral for z. So that first part will be 1 over 8 y squared z plus 1 over 6 y cubed z squared. We make replacements for y is equals to 0 and y is equals to 1. And then we now differentiate with respect to z. So this will be 12 over 7. Then, if I make replacements for 1, I have 1 over 8 z. And this for 1 becomes 1 over 6 z squared. I'm integrating with respect to z. So this becomes 12 over 7. Then this will be 1 over 16 z squared plus 1 over 18 z cubed. Make replacements for z0 and z1. So this will be 12 over 7. Then 1 over 16 plus 1 over 18. And therefore, the expectation becomes 3 over 7 times 17 over 36, which is actually 17 over 84. That is the expected value. We consider some properties of expectation. Property number 1, expected of xi is equals to integral negative infinity to infinity all the way to negative infinity to infinity of xi f x1 all the way to xn dx1 all the way to dxn. This is the same as integral negative infinity to infinity of xi fxi xi fi xi rather dxi. Thus, we note here that you can calculate expected of xi either from the joint distribution of x1 all the way to xn, or from the marginal distribution of xi. Let's prove that property. Now, integral negative infinity to infinity, integral negative infinity to infinity of xi f xi x1 all the way to xn dx1 all the way to dxn is equals to integral negative infinity to infinity of xi, then integral negative infinity to infinity, all the way to negative infinity to infinity, fx1 all the way to xn, dx1 all the way to dxi minus 1, dxi plus 1, all the way to dxn, then dxi. So that this is the same as integral negative infinity to infinity of xi, then fi, xi, this part here. Then the last part, the whole of this from here all the way to here is just this. Then dxi, which we are seeing now, the whole of this is just this. Property number 2, called linearity property. Linearity property. It states that integral negative infinity to infinity, all the way to negative infinity to infinity, of a1x1 plus all the way to plus anxn, fx1 all the way to xn, dx1 all the way to dxn is equals to a1 integral negative infinity to infinity all the way to negative infinity to infinity, x1 fx1 all the way to xn, then dx1 all the way to dxn, plus all the way to plus an integral negative infinity to infinity all the way to integral negative infinity to infinity, xn f x1 all the way to xn, dx1 all the way to dxn. So if you have constants, they just come out of the expectation as coefficients. Now multiplicative property. Suppose x1 all the way to xn are independent of x1, xq plus 1 all the way to xk, then expected of g x1 all the way to xq, then h xq plus 1 all the way to xk is the same as expected this square bracket. That is, we want the expected of the joint expression of g and h being two independent functions is the same as getting the expectation of each of the expressions xq, then multiplied by the expected of h xq plus 1 all the way to xk. In the simple case, when k is equals to 2 and g of x is equals to x, while h of y is equals to y, then expected of xy is simply the product of the individual expectations. That is, if x and y are independent, then you just get the joint expectation by multiplying the product of the individual expectation. We need to prove this. Prove expected of g of x1 all the way to xq, h of xq plus 1 all the way to xk is the same as integral negative infinity to infinity all the way to integral negative infinity to infinity of g of x1 all the way to xq, h of xq plus 1 all the way to xk, then the distribution x1 all the way to xk with respect to dx1 all the way to dxk. This is now equal to integral negative infinity to infinity of the partition. We again partition the joint distribution of all the random variables, so that we'll have g of x1 all the way to xq, h xq plus 1 all the way to xk. Then we have f1 x1 all the way to xq. We are now getting the partition. Then f of xq plus 1 all the way to xk. Then dx1 all the way to dxq. Then dxq plus 1 all the way to dxk. So we have partitioned the distribution of all of them into two parts, this part and this part. The same case with the dx's. So that this is equivalent to, because if we pick this part, remember even the integral symbol are partitioned. If we pick this part and this part, then we get the expected of gh, and then we can evaluate the expected of h. So this will be the same as integral negative infinity to infinity in both cases. Then we have h xq plus 1 all the way to xk. Then f of xq plus 1 all the way to xk. Then we have integral negative infinity to infinity all the way to negative infinity to infinity of g of x1 all the way to xq. Then the distribution f1, remember this is f2, f1 x1 all the way to xq. Then dx1 all the way to dxq. Close this. Then we have this other part, the dx all the way to the dx in terms of the partition for q, starting from q plus 1. So we have dx q plus 1 all the way to dxk. So whatever is in the square brackets is actually the expected of g of x, and therefore we have that this is equivalent to expected of g of x1 all the way to xq, then times the other part now, negative infinity all the way to negative infinity infinity of h xq plus 1 all the way to xk. Then f2 xq plus 1 all the way to xk dx q plus 1 all the way to dxk. So again, this other part is the expected of h. So we have then, the result is such that we have expected of g x1 all the way to xq multiplied by expected of h xq plus 1 all the way to xk. Let's look at properties of variance. Property number 1, variance of x plus y is equals to variance of x plus twice covariance of xy plus variance of y, where covariance of xy is the same as expected of x minus mu x, y minus mu y. And we prove that property. Variance of x plus y implies the expected of x plus y from definition of variance minus mu x plus y whole of this squared. Note the introduction of both the square and the curly brackets. The curly brackets are saying that we are squaring this expression. Now this is, first we define some expression. Mu x plus y simply implies the expected of x plus y, which is the expected of x plus the expected of y. So variance of x plus y being equals to expected of, introduce the curly brackets, we have x plus y minus the expected of x plus the expected of y, these two. Then we square this. We notice that by applying the curly brackets, we can be able to get an expression of the form expected of, by opening the curly brackets, we are going to have x minus, because we are having x plus y, then minus mu x minus mu y, then we are squaring this. So we can regroup them into x minus mu of x, then plus y minus mu of y, then we need to square this then. So treating these as a and these as b, then we are going to have expected of x minus mu of x squared plus twice x minus mu of x, y minus mu of y, then plus y minus mu of y squared. Then at this point, if we apply the expectation, this is just the variance of x. And then this is the covariance. So we have two covariance of x, y, and then this is the variance of y. Property number 2. The variance, the correlation between x and y is in the interval 0, 1, inclusive, and the absolute value of the correlation of x, y is actually 1. If there exists A and B such that probability of y is equals to bx plus A is equals to 1, where rho of xy is positive if b is greater than 0, and rho of xy, the correlation between xy, is negative if b is less than 0. Proof. Let u be defined by x minus mu of x, and v be defined by y minus mu of y. Let also g of b be equals to the expected of v minus bu squared, and this be greater than b for all b. We will pick minimization of the function g of b, so that if g of b is equals to expected of v minus bu squared, this should be, if we open the square part, then we have expected of v squared minus 2bvu plus b squared u squared. This is the same as if we take expectation, we have expected of v squared minus 2b expected of vu plus b squared expected of u squared. You notice u and v are random variables, while b is a constant, so that's why it's coming out. So taking derivative of this equation, of gb with respect to b, we have the derivative of gb will be equals to negative 2. This doesn't have b, so it disappears. Expected of vu plus twice b expected of u squared. If we want it minimum, then we equate it to 0. This b squared drop 2 and then the power minus 1. That's why we are having 2b. Now, implying that if we make b the subject of the formula and we want to minimize it, that means that b is equals to minimum of b, which is expected of vu all over expected of u squared. Since g of b should be greater than 0, then g at the minimum value of b should also be greater than or equal to 0. And therefore, gb minimum is equals to expected of v squared minus 2b minimum expected of vu plus b squared minimum expected of u squared, implying that this is equals to expected of v squared minus 2 expected of vu divided by expected of u squared expected of vu plus expected of vu squared expected of vu divided by expected of u squared. This one squared expected of u squared. I'm just making replacements for b minimum from here. So this implies that if we simplify this, we have it is equals to expected of v squared minus expected of vu, this one squared divided by expected of u squared, and this should be greater than 0. Thus, expected of vu squared divided by expected of u squared expected of v squared must be less than 1 for it to hold, or simply expected of x minus mu x y minus mu y, this one squared divided by expected of x minus mu x squared expected of y minus mu y squared, which is equals to the correlation between x and y must be less than 1. Hence the proof. We have property number 3. Variance of ax plus by is equals to a squared variance of x plus b squared variance of y plus 2ab covariance of xy. Property number 4, variance of a1x1 plus anxn should be equals to a squared 1 variance of x1 plus a squared n variance of xn plus 2a1 a2 covariance of x1 x2 plus all the way to plus twice a1 an covariance x1 xn plus twice a2 a3 covariance x2 x3 plus all the way to plus twice a2 n2 covariance of x2 xn plus twice an minus 1 an covariance xn minus 1 xn. And this can be expressed in summation symbol as summation I is equals to 1 to n of ai variance of xi plus twice double summation for I less than j ai aj covariance xi xj. So that this is the same as summation I is equals to 1 to n of ai squared variance of xi if x1 all the way to xn are mutually independent. That's the end of lesson 2.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.